One of the most serious threats to web applications and the underlying data contained in the web server are SQL injections. In this section, we'll talk about this common threat, including the different types of SQL injection attacks, the common attack methodology, SQL injection tools, and countermeasures. SQL, or SQL, is short for Structured Query Language. Because SQL is so commonly used, it's an important programming language to know as a developer. It's also one of the older types of code out there, and it's very widely implemented. So it's important for us to understand some of the workings of this as well. Because of its prevalence, it is a common target, and we've looked briefly already at some examples of injection attacks, but let's look more closely at some different types of SQL here. SQL is a standard of communicating for relational databases. And when we say relational databases, we simply mean a database of information that has organized contents which are related to one another, and those would be presented as a collection of tables. If you take a digital storefront as an example, we see an example customer database here from maybe somewhere like Amazon. Their relational database may contain things like the customer ID, the first and last name, the email address, passwords, physical address, and so on. So they may have a table like we see here, maybe called customer information, and that table is going to have rows and columns. Each individual box inside the database is called a data field, and typically one of the columns here with the data fields will be designated as the primary key. This primary key is what allows for a relationship to a different table in the database. So let's assume the customer ID is the primary key here. In order for a relational database to link together maybe customer orders that could be related to a particular customer, they might have a completely separate table for orders, which would also contain the customer ID field. So when we're retrieving orders for a particular customer, the primary key being the customer ID, that's what would be referenced, and this creates a relational database. So this is a way that we ensure that we don't have to reuse data and create databases that are larger than necessary. We use these relational forms of data. SQL uses various commands to perform operations on a database, including examples like select, update, delete, insert, create, and more. Applications use SQL commands for various things like login credential authentication, information retrieval for the data that a user has requested, for setting access levels to what the user is actually able to see in the database, and so on. SQL injection happens when web application input is not configured to properly screen out any unwanted SQL statements from the input box. That could be a username or a password box, and we call this input validation. So if the inputs are not being validated, that creates a potential SQL vulnerability. The lack of proper input validation is what creates the ability for malicious or unauthorized action to be taken against a database by inserting SQL language commands into that input box. Common reasons we see this used would be, of course, authentication and authorization bypassing, where an attacker is able to log into a web application without actually having any valid credentials. Data disclosure is also possible. This allows an attacker to view the contents of the database, including even the exact size of the database. And we have the potential for remote code execution as well. It's possible for an attacker to compromise the host operating system itself, affecting the system and any users who may try to access that. It's also possible that they may permanently embed some sort of code or action in there that will be executed against anyone who visits. In general, we can categorize SQL injection attacks into two broad categories. First, we have typical error-based SQL injection, where someone attempts to insert malicious strings into an input field in order to receive an error message. Now, as we've mentioned, proper input validation would not allow these types of attacks, and also things like proper error suppression that we'll talk about later on. The error message that is returned can give information about the database itself. In some cases, this alone is enough for attackers to enumerate the entire database. Of course, we understand that error messages are of legitimate use to developers of web applications, especially when they're building and troubleshooting. But for production applications, anything that we have public facing, if we have a publicly available web application these error messages should be disabled, or at the very least, those should be configured to be logged to an internal server somewhere that only the developer would be able to retrieve those from. So we don't want to stop error messages necessarily, but we do want to make sure that we are suppressing those properly and logging them to a secure location. If we go into our OWASP VWA application, let's scroll down a bit and let's choose this damn vulnerable web application, or DVWA for short. And the default login for testing this application here is going to be admin for the username and admin for the password, and that gets us logged into this web application interface. From here, if we look on the left-hand side, we have several examples that we can use for labbing. The top one, let's start here with SQL Injection. Now, the way that this web application sample is designed is if we actually enter a numerical input, let's say we enter the number 1 and we hit submit, you'll see that this returns back a first name and a last name along with the user ID that we entered. So if we know a numerical user ID, it will print back the first name and the last name. Now, this is a very simple example where the numbers are single digits, but let's suppose that we were looking at something that was long and randomized. Well, what happens if we try an error-based injection and we use one of our classic examples of entering a single quotation mark? Let's put that in and let's hit enter. And you'll see that we are brought to an error page. We have an error message letting us know that our SQL syntax was incorrect. It tells us to check the manual that corresponds to your MySQL server. So here we know we're using MySQL as the base. So this tells us that this is recognizing SQL commands from the user input and that it has no input validation in place. And that means the web application is susceptible to further SQL injection attacks. Ideally, we would not want this command to be recognized at all, and we additionally certainly would not want to present this error message back to the web application. In addition to error-based attacks, we also have blind SQL injection. We call this blind injection because we don't receive any specific error messages, or maybe the error messages are too general to provide any information. This is a more difficult type of attack because, as the name implies, we're working blindly. With these types of attacks, we are typically querying the database with true or false statements, and the answer or the response is going to be based on how the application handles those, and that will tell us more information. If we go back to DVWA here, let's choose our next option for SQL blind injection, and we'll take a look at this simple example. Let's begin by showing you the functionality again. Entering an ID will return back information to us. Now, if we try our single quotation here and we hit enter, this is what we want to see. This is how we want our web applications to interact with us. We don't get an error message, and we really don't get anything. We don't get any additional information as far as this user input goes. It just blanks out. It doesn't accept it. So we're working blindly here. We're working without any error messages when we test this out. Now, if we do go and use maybe our classic SQL injection command that we've looked at already, one quote or quote one close quote equals quote one, and we hit enter, you will see that we're able to enumerate this database and get that to dump out all the information. But again, we're working blindly here. We don't have any error messages that let us know about the version of the database in use or any of the operating system information. We simply have to use trial and error here. We can also perform SQL injection attacks as either in-band or out-of-band. The examples we've already looked at here are considered in-band attacks. We've looked at some of those throughout this course because we're retrieving data back over the same channel that we're using to interact with the database. In other words, maybe we're interacting with a web application and the web application itself is presenting information back to us. If we're putting SQL commands into a username or a password box in order to retrieve data, that's an example of in-band SQL injection. We also need to know about out-of-band SQL injection attacks, although notably these are not nearly as common, and that's because they're much more difficult to achieve successfully. They rely on the database server's ability to make DNS or HTTP requests in order for that data to be delivered back to the attacker. An attacker could send malicious code to a database, which could have instructions for sending data inside of the database, like usernames or passwords in there, as an outbound DNS request or an outbound HTTP request, which would go to a location of the attacker's choosing where they could obtain that data. Just as with other items that we've looked at in this course, there is a SQL injection attack methodology that we can follow as well. So let's talk about that. The first step is to test for SQL injection vulnerabilities. Essentially what we're doing is we're looking for entry points for our attack. Now we've looked at ways that we can do that through all kinds of different information gathering tactics already, but let's look at some ways again that we can do this specifically for SQL. So here we're back in DVWA. We looked at this in our previous video in regard to extracting error messages. And again, that's a common tactic that we would try when we're testing for vulnerabilities. As we've seen before, we can enter a single quote here and hit enter, and we're presented with an error message here. So this, of course, is a more generic error message in that it doesn't reveal a lot of specific information, but sometimes this can provide other information that we might find helpful, such as the database version, the operating system, and more. So this is one tactic that gives us more information about how we may be able to successfully craft an attack later in our methodology. We can also use a method if we go back here in our browser, and we can use a method where we actually modify the parameters. So if we enter the number 1 here and we submit, this of course is a valid request, a valid query that we've made. And we can actually try altering parameters for the query itself. And we can do that by either capturing those in something like Burp Suite and altering those and sending them over, or sometimes we can also do that in a browser. We can alter HTTP GET and POST requests in these ways in order to try and generate errors or to try and access unintended data. Now, if you notice our URL in our URL bar here at the top, one area that I'll point out is the ID equals 1. So we have an ID parameter referencing what we've put into our input box. So if we change that and we likewise put a single quote in up here and we hit enter, we do see that error message once again. Let's go back into our Mutility application and let's take a look at this user lookup web application example here from the perspective of SQL. So you can see that this particular web application is designed to be able to enter a username and a password, and we should be able to view our account details. So if we actually click this button with nothing inside, we of course get an authentication error, bad username or password, and below that we see there are results for no records found. Let's enter a single quote here, and let's try to view account details, and let's scroll down, and this time this gives you a look at a much more verbose error message. This reveals way too much information. In fact, we even see the specific SQL query listed here. We see the query select from accounts where username and password. So we can see that we are selecting a value. We see the select command. We're selecting a value from, and we can infer that we're selecting a value from a table called accounts. And we see where the username. So we can also infer that there's probably a column called username and there's probably a column called password here. So we do have some sensitive data information obtained. So now we understand how this query is constructed, and what we can do is change this where command. This where command is what makes this not true because we didn't enter a username and a password. So instead of where, we could use our classic 1 equals 1 logic to make a true statement. So let's go back up at the top. And again, our classic example of SQL injection, we can say 1 quote or quote 1 quote equals quote 1. And I typed that in the name box just so that you could see what that looked like. I'm going to type the exact same thing here inside the password box. Let's click View Account Details. And if we scroll down, now look what has happened here. Because we entered that true statement, this actually dumped out all of our username and password column data back to us. So this is a good example of an in-band attack where we're attacking and we're receiving data over the exact same channels, which would be our user input boxes here. Now we can also do this in an automated manner as well from Burp Suite. We've looked at Burp Suite quite extensively already. So let's open up our proxy browser inside of Burp Suite. I'm going to grab our URL from here. And inside of our Burp Suite, in the proxy browser, Let's paste this in. We'll go out to that. In our proxy intercept, we can see these being intercepted. So we see we've grabbed this get command here. And let's go back out to this, and let's just actually enter anything here. Let's say test, view account details. Of course, that doesn't work on our actual web application side. If we forward through this, we're going to see error messages here because that is not a valid account. We see authentication error, bad username or password, but that's totally fine. That doesn't matter to us. We're mostly interested in grabbing the syntax inside of this. So let's go back into Burp Suite and let's take a look at our HTTP history. We can see this here. We can see our GET request, which has our username field, our password field. And if we want to automate this, we can right click. We can send to intruder. We can jump over into our intruder. And of course, we can set our payload positions. We can clear out those automatic positions. We can add in username and password. We could go over to our payloads and we could load a list of payloads from here. We would do that as a simple list and we would have a text document. Most helpfully, that would be full of sample injection commands, SQL injection commands. I've talked about previously that you can reference various online cheat sheets for these well-known and documented SQL injection parameters for your testing. So that's a good idea. Keep a text document on your system with most of those popular SQL injection commands. Then with Burp Suite, you could simply load that list, and instead of having to manually type in all of these well-known commands, you could just do that here in an automated manner. This is something that we call SQL fuzzing. Once we have performed an assessment against vulnerabilities, the next step would be to actually launch a SQL injection attack. This would be one of the types of attacks that we've already looked at, either error-based attacks or blind SQL injection attacks. And the goals here are going to determine the type of techniques that we use for the attack. Maybe we're trying to bypass login, or maybe we just want to extract database information. Maybe we want to enumerate the database itself, or even deleting the database. And lastly, if we're successful in the previous two steps, the final step would be pivoting or advanced SQL injection attacks, where we're trying to interact with maybe any underlying hardware or software on which the SQL server is running. That could include injecting things like key logging devices, where we're capturing keystrokes on the system. Maybe we are planting Trojan malware and more. And that would also include denial of service attacks, such as buffer overflow situations. It's also worth noting that when an attack is being crafted and executed, it's important to understand the database structure and how that language is used. There are various iterations for database management systems out there, and they use different languages and different syntax, and the way that requests are interpreted are going to vary slightly between those. In addition to manual SQL injection commands, it's also helpful to use injection tools. Some of these we've looked at already. We've looked at using Burp Suite as a fuzzer to insert common commands, and we've also looked at SQL Map. So just to reiterate some of that, let's jump in here into our Parrot OS. And if you recall, in an earlier video, we looked at injection attacks, and we used this test website, testphp.vulnweb.com. And from here, if we choose maybe browse artists, this is going to bring up a list of artists. We can click on any individual artist. And if you'll remember, we were targeting this PHP artist equals 1. We found that very interesting. So let's revisit this just to reiterate how SQL Map works. Let's copy this and let's jump into our terminal here. Again, we saw the PHP extension. That is a very popular scripting language for web development. And this particular instance uses MySQL, this particular test website. So let's launch SQL Map by saying SQL Map. We want to say -u to indicate the target. We can paste in the URL that we copied previously. And one way we can enumerate that, we can say -dbs to search the database. We'll hit enter. And this will begin attempting to enumerate this resource for any databases that might be in place. We see that it is connecting to MySQL as the backend data management system, and it has returned a couple of databases back to us. We see again AccuArt and information_schema. So let's arrow up and we'll call out the database, AccuArt, and let's say we want to see the tables inside of that database. So we'll say dash tables, and we of course see 8 tables returned to us. Let's also arrow up, and let's also enumerate our columns. So instead of tables, we'll say dash columns and see what happens here. So now we see our columns output back to us, and if we scroll up, we can find the previous table we looked at, which was users, and we see there's a column there for username. So now we can get even more specific. Let's go back to the bottom. Let's say the database is AccuArt, the table is users, the column is pass. We saw a password column there, and the command we want to say is dash dash dump. And let's see if this dumps that out for us. And of course it does. We see the password is test. There's only one password stored in there. But again, that's how SQL Map works. That's one of our SQL injection tools. Another one I'll point out is something called the mole. Let me go out to a browser here, and I'll show you the GitHub page for the mole. You can see that listed here. It's a very similar tool. It's a Python-based tool, and it works in a similar manner as SQL Map. Now, this is not installed by default, so if you want to install that, you can search for the mole. You can find the GitHub repository, and under code, if we drop this down, you'll see we have an HTTPS link, which we can copy. We can go into Parrot Terminal. I'm going to clear off our screen here just to clean things up a little bit. And to install that, we would say git clone, and we would paste in the HTTPS link. Now, I do already have this. In fact, if I do an ls command, you'll see that I have a folder, a directory called the mole. You see that listed here in my output. So I can change into that directory. And in fact, in order to run the mole, I do need to do that. If I perform an ls command, there is a Python script in here called mole.py. So again, this is Python based. So I need to say python3 mole.py, and that launches the mole tool. Now let's go back into my browser here, and I'm going to once again just grab this URL that we've been testing against. I'm going to copy this, and back in my terminal, so this works a little different. It has a little different syntax. What we want to do is say URL, and we paste that URL inside of there. We hit enter, so that sets our URL target. Now, if I say schemas, in order to try and view the logical structure of the database, that's what schemas are. It's going to tell us we have a missing parameter, and it tells us that the attribute needle is required. So needle is the section of the URL that we're targeting. And if you look at this, the interesting section to us is this artist equals. So we need to enter that here in single quotation marks. Artist equals, we'll close that on each end with quotation marks. We'll hit enter. And now if we say schemas, we'll see the mole will begin working against this particular URL. And we're going to see some of the same things happening as we saw in SQL Map. We see it's trying a separator. It went from single quote to double quote. It's going to try some comment functions in just a bit. You'll see that it found the database management system MySQL. Now it's trying to inject using a comment. And we can see this continue to progress, trying to inject in certain fields. It looks like it found 3 injectable fields. It's trying a string union technique now. So this presents a little bit more information to us than MySQL does, in that we can actually see the steps it's walking through. It did spit out both of the same databases eventually. We see AccuArt and information underscore schema. Now what we can say is, if we want to see the tables, we can say tables, followed by the actual database. And let's see what that spits out for us. You can see it found 8 rows, and it's currently working on dumping those. And there we see our table with our 8 different rows inside. Now, if we want to see the columns, we can say columns, and we call out the previous name of the table, which is AccuArt, and we call out the column that we want to see. One of the columns here is users, of course. So let's say users. Let's hit enter. Now that has found 8 rows. It's working on dumping those out. And we see that the table users similarly has 8 different rows. Now, if we want to see the information from a specific row here, or from a subtable, we can make a query. We could say query AccuArt, which is the overall name of the table, users, and the value that we want to query. We've looked at password already. Let's try phone. We'll hit enter. And that should spit out a single phone entry, most likely for us. Yes, we do see one row. And there we see that. Now, we could, of course, do this for other information as well. If we arrow up, we can do that for email. We could do that for address, for the username. So there's our email address. Let's try CC. I assume that to be credit card. And we see that listed in here as well. Now, most likely that is hashed in some way, but we might be able to break that credit card hash and find out that information. So just a few automated options I wanted to point out in addition to Burp Suite that we've already looked at. We have SQL Map, we have the Mole, we also have standalone items like NoSQL Map. That's another GitHub tool that we can find on their repository. That's a good one. And there are tons of these out there. There are all kinds of different Python-based tools that work well inside of Kali Linux and Parrot OS. It's not a bad idea to use different combinations of these in addition to your manual coding skills in order to test out SQL injection vulnerabilities. Let's talk now about tactics for SQL injection evasion that we need to be aware of. Many modern networks are moving to signature-based detection systems. These are considered to be next-generation security devices, and they would include firewalls or intrusion prevention systems, or most commonly nowadays, a combination of those tools found on a single appliance. Signature-based detection is one of the most common techniques used to detect numerous types of threats, including many different types of malware, such as viruses, trojans, and more. These security systems have a predefined repository of static signatures. And by static signatures, we're referring to fingerprints. These represent known network threats. These threats are different from one another because of their unique encoding. And because they're different, they're each going to have a different fingerprint. When we're talking in terms of SQL injection protection, these mechanisms would have a database of popular or common SQL injection commands based on their signatures. And anytime traffic matching that signature attempted to pass through, let's say, a firewall, then that traffic would be denied. Signature-based detection is one of the biggest considerations for evading security measures when it comes to SQL injection. So let's look at a few common evasion techniques for bypassing signature detection. First, we have the use of various encodings. This can include things like URL coding as an example. This is performed by replacing characters with their ASCII codes in hexadecimal form, and we precede each one of these with a % sign. So if we have an original query that looks like this, with URL encoding, that would look like this instead, where the spaces are represented by the %20 character. They could also use hexadecimal encoding as well, which would make the exact same input look as we see here. Now, these are just a few examples, and there are various types of encoding like these that could potentially allow SQL injections to evade signature detection. Because again, if we're changing the actual format of the data, we're essentially changing the fingerprint. We're changing the signature. Another one is something we call white space diversity. This means we generate additional white spaces between SQL commands or strings. If you think of a common signature that may be blocked, like union select, if we insert a lot of white space in between those words, then we've again changed the overall signature. We've changed the fingerprint of the command, but the command may still execute as we would expect it to. Character case variation is another technique. As a default deployment option, SQL is case insensitive, meaning that it pays no attention to whether or not a letter is upper or lowercase, so it doesn't matter as far as sending in commands goes. Now let's say with a next generation device, we've configured that to block a couple of queries as we see here. We're blocking that as an all uppercase query, and we're blocking it as an all lowercase query in regard to the signatures. But what if an attacker mixes upper and lowercase lettering? That means if they're able to do that and this isn't specifically blocked, or there's no detection mechanism for that, they may be able to bypass the signature detection. String concatenation is the process of appending one string of data to the end of another string of data using a special operator, such as the plus sign. That's a common one that we see, and we see concatenation used in lots of different programming languages. Comparing the original union select, that might be broken down into concatenated strings, as we see here on screen, where the plus sign operator would be used by a SQL Server database for concatenating, or in other words, for combining those strings. There are other options besides the plus sign as well, such as with Oracle servers, which use the double vertical bar to denote concatenation. So you want to be aware of what the underlying system is to depend on which form of concatenation you're using and which operator. There are also more traditional means for this, like IP fragmentation. IP fragmentation applies to more than just SQL commands, and in fact, this is a common attack tactic in general for all types of malware. This is where an attacker intentionally splits a packet into multiple fragments and sends those fragments in maybe in a different order. They might send those in, for example, in reverse order. Typically with IP fragmentation, the reassembly occurs at the final recipient of the message, after all of the fragments have arrived. That means the security devices themselves may not be configured to detect these attacks. If they're not configured to reassemble and inspect packet fragments that arrive before passing them on, that means the attack could make it through the security device. And of course, it's worth noting here that many of our next generation devices are getting really good at detecting these types of things, so it's good to try combinations of these techniques as well. And not only these techniques, but other popular evasion techniques could be used as well. These are just a sample of some of the most common ones that we see, giving us the best chance of making it through a security checkpoint. As we've seen throughout this section, SQL injection attacks have a wide variety of techniques that will allow them to be successful. So let's go through some common countermeasures that we need to know about in order to protect web applications. The first consideration, as we've seen with many countermeasure categories, is training and awareness. In order for our web applications to be as hardened as possible, everyone in the creation and deployment of a web application should have an awareness of common attacks and security risks. That would include those for SQL injection. This includes system admins, DevOps teams, and of course internal security teams as well, those working on the typical network infrastructure. As we've mentioned, security should be a consideration from the very beginning of the development process, and that should be maintained throughout the life cycle of the web application, including the testing, deployment, and update phases for the application. Giving these internal teams an awareness of the potential risks can help circumvent many of the implementation errors that we've seen in play previously with our SQL injection section. We should also inherently distrust all user input, both internal and external users. In other words, we want to have input validation in place. This will verify whether or not the data that a user is attempting to submit into the web application is accepted or not. For example, any user input that contains any sort of SQL syntax or query should obviously not be accepted as a legitimate input. We should make no assumptions about the size or the type of data that's being received by our applications as well. And that's because inputs can be obfuscated through various means that we've looked at previously, such as using encoding or concatenation. Within the application itself, we have a couple of different approaches for input validation, and those are either blacklisting or whitelisting. These are different forms of denying an input based on parameters that we have determined. Blacklisting means that we're specifically disallowing input that we have identified as being malicious. This is the easier way to accomplish input validation because it does require less work, and we often also have less false positives. But it can also be defeated easier using some of the evasion techniques that we've already looked at, where we're maybe obfuscating the data that we're sending in to the web application. Whitelisting is the stronger approach. With whitelisting, we have a specific list of characters that we are allowing, and nothing outside of that list would be accepted as an input. This is more restrictive, as you can imagine, but it is more difficult to enlist because we need to take every potential legitimate input into consideration and identify that. Also, as we've looked at previously, we want to make sure that database error information is not being disclosed to the end user of a web application. Error messages can reveal sensitive information about the database itself, so when we have a production application, we want to make sure these error messages are not being presented to users. Error message logging is still important from a security and troubleshooting perspective, but we want to make sure that these are being logged internally to a secure location rather than being presented publicly. Using the most up-to-date software and technology is also critical. Older standards and environments are going to have many known vulnerabilities that are well documented. So if we're running something other than the latest version, we're potentially opening ourselves up to threats. Newer development technologies will inherently have more stronger SQL injection protections already built in, and those are also going to receive more consistent updates and patches as well. As for the data inside the server that is being queried by our application, we want to enable proper protection mechanisms, particularly for any sensitive data that may be stored there. That would include usernames or passwords, among other things. We want to make sure that we're using strong hashing algorithms to obscure that data, such as SHA-256. We would want to use that rather than a weaker algorithm, maybe like MD5, which can be easily reversed. We also need to think of countermeasures from the infrastructure perspective as well. The networks on which these applications live should also be hardened, including things like making sure the web application server is behind a properly configured firewall. Typically, the only clients that should need direct access to the SQL server are the network administration and staff, so all other access should ideally be blocked. SQL Server listens over specific ports that can remain open, but everything else should be locked down. This can mitigate malicious scripts from being sent to the server itself. And of course, all other network devices through which the data travels should also have their security preferences properly configured, and that would include switches and routers. And some final considerations include, of course, making sure we are regularly patching the software. With this procedure, we should also be regularly scanning for any previously undiscovered or new vulnerabilities that may be in place. We want to use our manual SQL skills and also automated tools that we've looked at such as Burp Suite and OWASP Z Attack Proxy or ZAP. Those can help us identify vulnerabilities in our web applications, decreasing the likelihood of attacks.